Okay, so my name is Liliana, and I will be your host for today's webinar. So welcome and thank you for joining the webinar entitled Advances in Hamiltonian Transport and Chaotic Dynamics. So please be aware that this webinar is being recorded and the recording will be available as soon as possible. I will introduce MDPI and our journal, and then I will introduce the chair. Okay, so MDPI was founded in '96 in Basel, Switzerland. It's a pioneer in scholarly open access publishing, and it has the mission to foster open scientific exchange in all forms across all disciplines. We have almost 500 diverse and open access journals, from which 9 are conference journals, and we're supported by almost 300,000 academic experts who share our mission, values, and commitment to providing high-quality service for our authors. Mathematics is a peer-reviewed open access journal which provides an advanced forum for studies related to mathematics. We collaborate with 2 societies, the European Society for Fuzzy Logic and Technology and International Society for the Study of Information. They are affiliated with mathematics, and their members receive a discount on article processing charges. Okay. This is the program for today's webinar. So after I introduce the chair, he will introduce the speakers. After each presentation, there will be Q&A part. Each presentation will take about half an hour. So if you have any questions during the presentations, feel free to post them in Q&A box at the bottom of the screen. And please remember to mention the name of the speaker to whom you're addressing the question. Okay, now I will introduce the chair. So Dr. Antonopoulos is a lecturer at the School of Mathematics, Statistics, and Actuarial Sciences, University of Essex. He obtained his bachelor's degrees in mathematics from the University of Crete and his master's degrees and PhD in applied mathematics from the University of Patras, Greece. His PhD focused on the stability and chaos in multidimensional Hamiltonian systems and their transition to statistical mechanics. He was a postdoctoral researcher at Université Libre de Bruxelles in Professor Gaspar's group, where he published work on Hamiltonian systems and statistical mechanics. He later joined Professor Van de Wiel and Professor Buti's group at the University of Patras under the European Complex Matter Program. So from 2012, he was a researcher fellow at the University of Aberdeen, working on information dynamical approaches to complex systems. Since 2015, he has taught and conducted research at the University of Essex, focusing on dynamical systems, chaos theory, information theory, computational neuroscience, and complex networks, with applications to brain dynamics and epidemic modeling. He's a member of the LMS and IMA and serves as editors for scientific reports, Frontiers in Computational Neuroscience, and Open Physics. He has authored 59 journal publications, 9 conference papers, book chapters, and delivered 59 talks, 19 invited. He has organized sessions at conferences and taught advanced courses on complex systems at summer school and PhD programs. With an H index of 24 and over 2,800 citations, he currently supervises 3 PhD students and collaborates internationally to advance mathematical modeling of complex systems. So I would like to thank the chair for organizing this and speakers as well. And now, without further ado, I will give the floor to the chair.
Okay, thank you so much, Liliana. I hope you can all hear me. And I would like to thank, in particular, Liliana, and also the host of this webinar, and MDPI in particular, who approached me and invited me to organize this webinar. I'm really happy to be able to be with you today and offer this webinar to all of us. I'm really happy to see we have so many attendees, and I would like to thank them all for joining today. And I hope you will really have some enjoyable time listening to this, participating in these discussions, and and the very nice presentation that we're going to have. So we're going to have 3 presentations today. And the first one will be delivered by Professor Edson Denis Leonel. And he will be discussing second-order phase transitions in chaotic systems. That will take place for about 30 to 35 minutes. Then we'll have a Q&A session where we will be discussing questions or anything related to the presentation. Then after the first Q&A session, we're going to have the second presentation by Professor Joelson Dayvison Veloso Hermes, again from Brazil. And he will be talking about invariant curves in Hamiltonian systems via Slater's theorem. That will take about 30 to 35 minutes again, and then we have another Q&A session to discuss questions on the presentation. And then finally, we're going to have our last presentation delivered by Dr. Mateusz Roliv-Sales, who is a postdoctoral researcher at the University of Essex. And he will be presenting on the recurrence time entropy as a diagnostic for stickiness in weakly chaotic dynamics. Again, it will take about 30 to 35 minutes, and then we'll have our last Q&A session before concluding the webinar today. So thank you everyone again for joining, and I'll pass the floor now to our first speaker, Professor Edson Denis Leonel, who will be discussing second-order phase transitions in chaotic systems. Thank you, Dennis.
Hello, Chris. Hello to everyone. Can you see my screen?
Yes.
Okay, very good. So I'm very delighted to be here with you today, and I will share some of our results we obtained about some scaling properties, particularly the one discussing a second-order phase transition in chaotic systems. So the title of my talk is Unrevealing the Mysteries, Exploring a Second-Order Phase Transition in Chaotic Systems. Well, first of all, I would like to congratulate Professor Chris Antonopoulos for this very good initiative to promote mathematics via this webinar, particularly discussing the advances in Hamiltonian transport and chaotic dynamics. Very good initiative, and I hope this topic will be discussed very much indeed. So for this talk, I will particularly use the tools from statistical mechanics involving scaling properties, critical dynamics, homogeneous and generalized function to characterize a very challenging problem in nonlinear dynamics. That is a phase transition from integrability to non-integrability. That is a connection between statistical mechanics and nonlinear dynamics. To start with, I will just present the goals of my talk. First of all, I would like to discuss a phase transition, then from integrability, discussing order and regularity to non-integrability, particularly the chaos dynamics in a two-dimensional mapping. And for doing this, there is a set of 4 main questions to be answered. The first one is the identification of what is called broken symmetry. And I will argue that we can see 2 symmetries in the system which are destroyed at the transition, characterizing then a broken symmetry. The second one is definition of what is called an order parameter, and also how the order parameter behaves as the function of a variation of the control parameter, which is called susceptibility. And there is an interesting result from statistical mechanics that the order parameter goes continuously to 0 at the transition. At the same time, its susceptibility diverges in the transition. This is a clear signature of a second-order phase transition. There is a third question to be answered, which is the discussion of the elementary excitation, of course, leading to the diffusion. And finally, the fourth question is the discussion of topological defects, which, of course, impacts in the transport of particles, and it leads to an interesting actual problem in nonlinear dynamics, which leads to the so-called stickiness effect. Okay, just to remind you about this phase transition, I'm showing here a diagram where in the vertical axis we have pressure, and in the horizontal one we have the temperature. This is a typical diagram for a fluid. We see here continuous lines separating different states, from solid to liquid, from liquid to gas, and from gas to solid. If we cross this continuous line from one side to the other one, as for example, from solid to liquid, we go melting. And if we go liquid to solid, we go freezing. A crossing from this line gives a first order phase transition. That is a discontinuity at the first derivative of the free mean energy, indeed Gibbs energy. If we go to this point here, which is called critical point, there is no first order phase transition anymore. There is a coexistence of states. And this point here is defined as a second order phase transition. In a second order phase transition, there is a discontinuity at the second derivative of the free mean energy. However, in this problem I'm talking today, there is no explicit free mean energy. Then we have to go for different aspects to characterize a continuous phase transition. If we consider this diagram, this point here where it's plotted the critical point is the place where I'm discussing our results today. Okay, let us go then to the specific. Let us start with an Hamiltonian, 2 degrees of freedom Hamiltonian system, which is composed of 2 pairs of dynamical variable, let's say I1 theta 1, I2 theta 2, and this Hamiltonian is composed of 2 main parts, H0, which is a regular part, is an integrable part, and there is an H1, which brings all the criticality and is controlled by a counterparameter epsilon. If epsilon is 0, the system is integrable, then regular. If epsilon is different from 0, we have a mixed phase space, therefore we have a non-integrability in the system. But if you see here, we have a flux of solution which lives in a 4D dimension. So it's a flux of a 4D. And we cannot figure out exactly what is a 4D in a 3D space. Then, because this Hamiltonian is time independent, we may take some advantages of this and rewrite the Hamiltonian eliminating one of these 4 variables, let's say I2. And then the Hamiltonian is here written in terms of only 3 dynamical variables, I1, theta 1, theta 2, because the energy is a constant, right? So by this transformation, we reduced the flux of solution to live in a space of 3D. If, however, we intercept this 3D flux of solution by a plane, which is called surface of recession, also known as Planck recession, the points where the flux intercept the plane are mostly described by a generic 2-dimensional mapping relating I, n, and theta n to in plus 1 and theta n plus 1. Of course, there is a set of 3 functions, non-linear, of course, non-linear functions of their dynamical variables, h, capital K, and p. And because this mapping came from a Hamiltonian, there must exist an area preservation in the system. And how can we impose area preservation in this mapping? It is obtained via the determinant of the Jacobian matrix. And even though we do not know what the functions h, k, and p are, but there must they have to follow this this expression, derivative of p with respect to theta n added to derivative of h with respect to in plus 1 should be 0. This is an imposition which comes from the determinant of the Jacobian matrix equals to the unity. Well, okay, for this talk, I will concentrate on a function h as a sign, because it is a continuous and it has all derivatives also continuous. It is limited, well behaved, and it is also the first term of Fourier series in a sine function. We will set P as 0 just to eliminate this counterparameter from the second equation of the mapping theta n plus 1. And we will define and we'll choose a family of nonlinear functions via this capital K as 1 over in plus 1 to a power of gamma. And we impose that gamma is a non-negative number, just to guarantee that this term in plus 1 lives on the denominator of this function of this ratio 1 over capital in plus 1. If we incorporate these functions into the mapping, we end up with this very interesting mapping. in plus 1 is equal to in plus epsilon sine theta n. Theta n plus 1 is a theta n plus 1 over capital in plus 1 to a power gamma modulated to pi. That means that the phase space lives in a cylindrical shape. It has cylindrical shape. Let us try to discuss about the symmetry of the system, which is broken now. Let us concentrate first on this ratio here on the second equation, 1 over capital in plus 1. If this term in the denominator is sufficiently close to 0, I mean very small, the ratio becomes large. If the ratio becomes large and is added to theta n, and since this the topology of the phase space is cylindrical, it implies that theta n plus 1 can in principle make very many turns in the phase space, in the sense that theta n plus 1 is uncorrelated to theta n at the limit of in plus 1 sufficiently small. So if we do not have correlation between theta n plus 1 and theta n, and considering that theta is an argument of the sine function here, sine behaves as a pseudo-random generator. And because this property of the sine, given the uncorrelation between theta n plus 1 and theta n, the first equation of the mapping behaves mostly like an equation of a random walk particle. And it gives the diffusion of the I along of the phase space. Therefore, for capital in plus 1, for capital in plus 1 is small, it implies that we have diffusion on the capital in along of the phase space. Okay, and since the capital in plus 1 diffuses, we can interpret this diffusion as an increase in in plus 1 along of the phase space. The term 1 over capital in plus 1 no longer becomes large along of the diffusion. And when this term here becomes well behaved, correlations in the phase space appear, and these correlations are mostly seen in the phase space via the existence of periodic islands, also called KAM islands, and invariant spanning curves, as they are shown in this plot here on the phase space. So in the vertical, we have the action, and on the horizontal, we have the angle theta, which is modulated to pi. So this is a cylindrical topology on the phase space. We constructed here this phase space for a control parameter epsilon 10 to a power of -3. So we see here a cloud and dense set of points in the phase space, which is mostly characterized by a chaotic C. If we start with a very close action from 0, we see the diffusion on the phase space. Eventually, it approaches to the existence of KAM islands. Particle moving in the chaotic dynamics cannot penetrate on the KAM islands, also called periodic islands, and cannot cross on these red curves here, which are called first invariant spanning curves. They work mostly as barriers on the phase space, do not allowing the particle to cross through because of the area preservation on the phase space. So we see here that the phase space is mixed with the existence of chaos and periodic islands on the phase space. When we plot the phase space for a control parameter epsilon equals to 0, we see only parallel lines on the phase space this phase space then is called as foliated, which is regular, well-defined. And we see here that when epsilon is different from 0, we have a clearly broken symmetry on the phase space. From regular parallel lines on the phase space, we see here mixed phase space with chaos, periodic islands, and invariant spanning curves on the phase space. That is a clear answer for the first question, identification of the broken symmetry on the phase space. But there is more than this on the phase space. If we look at the first equation of the mapping, capital In plus 1 equals to capital In plus epsilon sin of theta, when epsilon is equals to 0, we have an algebraic symmetry of the first equation, which is completely destroyed when epsilon is different from 0. So we have here two symmetry breaks on the system. One imply the other one. The first one is in algebraic, therefore a very robust symmetry which is destroyed, and its consequence on the phase space. So the first question is therefore answered by the identification of the broken symmetry. Let us move on and discuss now about the order parameter. When we are studying, let's say, investigating chaotic dynamics, a natural observable to measure is the so-called Lyapunov exponent. If the Lyapunov exponent is a positive for a dynamical system, we have loss of predictability of different initial conditions in the phase space. If we start with two different initial conditions very close to each other and allow the time to evolve, they may stay close for a while, and eventually they spread, they separate from each other. And then if we know where one of the dynamics is along of the phase space, you cannot say absolutely nothing about the other one. This exponential spread of two nearby initial conditions yields in a positive Lyapunov exponent, which is basically shown on this plot here on the vertical axis for an ensemble of different initial conditions along of the chaotic C. But the most interesting result for this plot here is that positive lambda varies very close, very small. I mean, it's a small variation from about 1.75 to about 1.5. That is about a variation of 16% on the vertical axis. But if we look on the horizontal axis, which is plotted logarithmic spaced, we see here 1, 2, 3, 4 orders of magnitude. That is a massive variation of the control parameter. And for this massive variation, the positive Lyapunov exponent is about a constant. But worse than that is that in a second order phase transition, the order parameter must go continuously and smoothly to 0 at the transition. And looking at this plot here, there is absolutely no glance that the positive Lyapunov exponent is approaching 0. So I'm afraid to say the positive Lyapunov exponent, even though is a very good observable to characterize chaotic dynamics, it is not a good candidate to be an order parameter for this classification, for this investigation. But since we are investigating chaotic diffusion, a most natural observable to be characterized is how the dynamical variable action I behaves along of the phase space, which is defined here as I root mean square. This observable is constructed via two different types of averages. One average is so-called Birkhoff's average, which is it is obtained an average over the orbit, an average over the time, while the second one is obtained via an average over an ensemble of different initial conditions. If we plot I root mean square against n, we see here for two different control parameters that the curves start to grow with a parallel and eventually after passing from a crossover iteration number, they bend toward a regime of saturation. And as soon as we change the control parameter, the curves have this similar behavior, but they are separated from each other. This kind of behavior shown in this figure here is typical from scaling dynamics. They have similar behavior, but shifted from each other. And that can be described by as a so-called homogeneous and generalized function, which is a very powerful tool used in statistical mechanics, which we are importing from statistical mechanics to characterize specifically this problem in nonlinear dynamics. So for a long enough time, we end up with this saturation dynamics, which marks the stationary state in the diffusion, which is marked by I sat, which is proportional to epsilon to a power of alpha. For a short time, we see that the curves behave as a power law. Therefore, I root mean square behaves as n epsilon squared to a power of beta. If we measure beta by a power law here, doing a power law fitting, it goes an exponent 0.5, which is very close to what we observe in normal diffusion in random walk problem. And the crossover iteration number is scales with epsilon to a power of z. We see here that z, beta, and alpha are the so-called critical exponents, and they must be somehow related among each other via a scaling law. The behavior described by I root mean square can therefore be described using this homogeneous and generalized function. It is not the scope for this seminar to show all these calculations, but importing the formalism from statistical mechanics and the fact that I root mean square is described by an homogeneous and generalized function, we end up with this very nice and interesting scaling law, z equals to alpha over beta minus 2. Therefore, if we know any two critical exponents, the third one is defined by this critical this scaling law. The critical exponent alpha is obtained analytically via the mapping, which also transcend the object of this seminar here, but it's written as 1 over 1 plus gamma. And since gamma is a non-negative number, alpha lives in the interval between 0 and 1, and z is obtained as minus 2 gamma over gamma plus 1. Okay, if we are considering that the particle along of the phase space is diffusing as a random particle, it's natural to obtain the probability density to observe a certain particle at action A in the time n. And this probability density is obtained via the so-called diffusion equation. So for resolving the diffusion equation, we have to identify what is the diffusion coefficient d, which comes from the first equation of the mapping, is epsilon is square over 4, therefore is a constant, where we assume that there is a normal diffusion on the phase space. Since the particle is moving confined between minus I Fisk and plus I Fisk, which are barriers on the phase space limiting the diffusion of the phase space, this is the domain where the particle can move, where we are imposing the validity of this diffusion equation. We have also to impose boundary conditions, which are defined as the derivative of p with respect to I, evaluated at plus and minus I Fisk equals to 0. That means there is no flux of particles crossing either the positive or the negative side of the phase space. Otherwise, if these conditions would be violated, of course, we are violating the Liouville theorem. And we are choosing all the initial conditions set at I equals to I naught at the time t equals to 0, which is a delta function. Okay, if we do all these calculations on the diffusion equation using the technique of variable separations, we end up with this very interesting expression for the probability distribution. There is a stationary state here, and there is a transient term, which marks the regime of growth and approaching to the saturation. For n sufficiently large, this transient term here disappear, and we end up with only this stationary term here on the probability density. Okay, if we have the probability density along of the phase space, we can measure all the observables on the phase space. So what is the behavior of I squared? Is the integral of I squared PDI DI evaluated between minus I fisc to plus I fisc. And this, there is a very nice, interesting expression here. And the most beautiful result is shown by this continuous curve here, where we choose specifically initial actions to show two different scalings on the diffusion. And when we define dimensionless axis, all of these curves overlap onto each other into a single enhanced universal plot as typical and characteristic of phase transitions. So what is a candidate to be an order parameter? The candidate to be an order parameter, which ends up to the answer to the second question, is I sat proportional to epsilon to a power of alpha. And we see when epsilon goes to 0, the order parameter approaches 0 continuously, which is a very good indicative of a second order phase transition. But there is more. If we look at the susceptibility, which is calculated as the derivative of I sat with respect to epsilon, we end up with this very interesting expression here. And if you see the exponent of the parameter epsilon is non-negative, therefore this term here it lives on the denominator, and when epsilon goes to 0, this susceptibility explodes, it diverges. Since gamma is a non-negative number, in the limit of epsilon approaching 0, the susceptibility diverges, which is a clear signature of a second order phase transition. Let us discuss now about the elementary excitation of the system. Just to remind you, this is a clear expression of the mapping. We have here epsilon controlling the intensity of the nonlinear function sign. It works somehow like a step length for the diffusion of this in plus 1. And if we start with an initial condition close to 0, the particle along of the chaotic C can only diffuse because epsilon is different from 0. So the elementary excitation imposing the diffusion of the particles is clearly observed by the counterparameter epsilon. So epsilon is the own elementary excitation of the system, leading to the diffusion on the phase space, right? So this is the answer for the third question in defining the elementary excitation of the system. Let us go then to the fourth question with the topological defects. Of course, imposing the transport of particles, the impact of transport of particles in the phase space. Just to remind you, there is a plot of the counterparameter, a plot of the phase space for the counterparameter epsilon 10 to a power of -2 and 10 to a power of -3. We see here clearly a chaotic C, which is limited by the invariant spanning curves, but which changes from position as the counterparameter is varied. But the most clear evidence in the phase space is the existence of KAM islands, right? There is an interesting result known in the literature that when a particle moving close to the periodic island, if it passes close enough to the periodic island, it could be trapped for a while. And this trap affects the transport of particles in the phase space. And this change on the probability distribution of the phase space could affect the behavior of the diffusion on the phase space. And as I will argue, the existence of the periodic islands, mostly characterized by the KAM islands, are also related to the so-called topological defects on the phase space. How can we measure this local trapping? So consider here we have a phase space for a parameter 10 to a power of -3, and that we define two different windows of escape on the phase space. The red curves shown here gives a window, an area on the phase space where by eyes we cannot see periodic islands. And however, if we go to the blue domain, we see here some periodic islands on the phase space. What is the observable plotted on the right-hand side? It is so-called survival probability. How can we obtain this survival probability? Let us start with a very large ensemble of different initial conditions along of the phase space with an action very close to zero and allow the dynamics to evolve. If a particle crosses these red curves either on the positive or on the negative side, we assume that the particle escaped from the region, from the domain. Therefore, the particle did not survive the dynamic. If the particle stayed trapped along of this chaotic domain here, we allow the dynamics to run more. Okay, so the red curve on the right-hand side is fitted by an exponential decay, and exponential decay is known in the literature to be typical from fully chaotic dynamics, while this changeover here from exponential decay to a slower decay is a characteristic of a stickiness effect on the phase space. We started here an ensemble of 5 times 10 to a power of 8 different initial conditions. And for this ensemble, only about 10 particles stayed trapped along of the phase space by islands which cannot be seen by eyes. However, if we go for a larger domain on the phase space, the blue curve show here that about 10 to a power of 3 particles are now trapped on the islands. So the islands indeed affect the transport of particles on the phase space, affecting the probability distribution of the particles on the phase space, and the islands behave somehow like a topological defects, therefore affecting the transport of particles on the phase space. So this is the answer for the 4th question used to characterize the phase transition in the phase space on the system. So I'm coming to my conclusions, Chris. We studied a phase transition from integrability to non-integrability, and all of the observables allow us to conclude that transition observed is a continuous phase transition, since the order parameter goes continuously to 0 at the same time its susceptibility diverges at the transition. There is a set of different applications, as for example, the formalism can be used immediately to characterize a transition from limited to unlimited diffusion, which is clearly seen in dissipative standard mapping and also in time-dependent periods. But the application goes far beyond. As for example, we may see phase transition from material science and engineering. We may develop more efficient electronic devices via technological innovations. There is applications of diffusions in biomedical, in pharmaceutical science, in climate dynamics, sustainable energy technologies, in emerging technologies such as nanotechnology, quantum computing, and photonics, and also phase transitions from modeling dynamics in diseases, particularly epidemics and so on. So I will just take the opportunity to promote two books from which we published last years and discuss about some of these results we discussed here: dynamical phase transition in chaotic system by Springer and scaling laws in dynamical systems. So I'm now in Institute of Geosciences and Exact Science, and we have a group for investigation in complex systems and nonlinear dynamics. And I kindly invite you to follow us on Instagram via this hashtag here. So thank you very much indeed, and I'm open for questions.
Thank you very much, Professor Leonel. That was a really very nice presentation of this subject, which is very fascinating. And I hope that our attendees have some questions to ask. If you do have some, please write them on the chat box, and then I will pass them to Professor Leonel to discuss them further. Any question to discuss? Oh yeah, there is one. Thank you very much, Kumar. So Kumar is asking, can we model the spread of infections or immune response more accurately using chaos theory?
Well, the answer is the following. It depends. Thank you very much, Kumar, first. It depends on how you are describing the system. We have to look at carefully how is the dynamics described, how is the environmental, if we have somehow boundary conditions or eventually initial conditions. It depends on the type of dynamics. If you have interacting particles, I mean, it is the answer is not so easy to give without a clear scene in the mapping or in the system or in the problem itself. I would say this.
Yeah, thank you very much. Any other question? If not, just to give more time to this, I would like to discuss the important effect of topological defects in the diffusion processes. So if we can go back to the slides in the presentation where you show the effect of the topological effect.
Yeah, this one.
Yeah, for example, this one. Yeah. So I think it's very interesting what's going on at the level of individual trajectories in the neighborhood of these stability islands of stability. And I would like you to comment a little bit more on the specific dynamics and how these influence the diffusion the diffusion parameter in the diffusion equation. So we discussed that the diffusion parameter in the diffusion equation is constant. And I think it was 1 over epsilon square or something. So in general, a constant number, right? But I think
yes,
in the case where the trajectories evolve for long times in the neighborhood of these islands of stability, probably this diffusion coefficient is not constant anymore, but it's probably a function of another variable. But yeah, if you could just discuss this, because I think it's very important for when it comes to phase transitions in general.
Yes, well, thank you very much, Chris. That is a very nice and very good question. Well, if we see here, for example, on the red curve, since we started with an ensemble of 5 times 10 to a power of 8 initial conditions, and we see only about 10 initial conditions trapped somewhere, which we cannot see clearly on the phase space. This is only 1 order of magnitude against 8 orders of magnitude. So the perturbation is small in the probability distribution function, therefore does not affect how the I root mean square behaves on the phase space. However, this changes a lot when we go to the presence of the island. So we see here on the region marked by the two blue curves, there is now 3 orders of magnitude of particles which stay trapped somewhere along of these periodic islands. But because we are considering 10 to a power of 8 initial conditions, we still have 3 orders of magnitude against 8 orders of magnitude. It still is a small influence, a small perturbation on the probability distribution function, but it is already seen. So coming straight ahead to your point, to your question, yes, the answer is yes. When the particle passes very close to the periodic islands, the diffusion coefficient is no longer a constant, but it turns to be somehow a tensor, and it depends on the local structure of the island, of course, depending on the boundary condition, because the chaotic sea cannot penetrate the island. So it depends on the shape of the island. In the islands, of course, they change from one to the second to the third orientation along of the phase space. I would say that this is still an open question. This is still an open problem to be investigated. And I agree with you that the understanding of how the microscopic dynamics would affect the macroscopic dynamics. This is a connection that must be made between local dynamics, influenced by specific orbits, specific initial conditions, and how these microscopic orbits would, I would say microscopic states, would affect the macro states of the dynamics. I would say that this is an open problem, and I hope that answers along of this point, along of this direction came within the next years.
Okay, thank you so much, Professor Leonel. Is there any other question? Anything you would like to discuss? Okay, I think there is no other question. So then we could probably move to the next presentation. So let's thank again Professor Leonel for this fascinating and exciting presentation, and move on now to the second presentation by Professor Joelson Dayvison Veloso Hermes, and he will talk about invariant curves in Hamiltonian systems via Slater's theorem. I think this is also related to the presentation by Professor Leonel. So thank you very much, Joelson, and looking forward to your presentation.
Good morning or good afternoon, depending on you are. First, it's a pleasure to me to be here with you today and talk about my work. The topic I choose to talk today is exploring invariant curves in Hamiltonian systems via Slater's theorem. First, my presentation is organized as follows. First, I will talk briefly about invariant curves and their importance in the context of dynamical systems. Next, I will present Slater's theorem and the method that use this theorem to study these curves. After that, I will show some applications for this method, and finally, I show some conclusions. In the context of dynamical systems, invariant curves are subsets of the phase space that are preserved by the dynamic of the systems. In other words, one condition on the curve stays on the curve. In quasi-integrable systems, such as Hamiltonian systems, close to the integrability, invariant curves appear that are tori and that corresponds to quasi-periodic motion. This is an important condition for apply the method. But why study these curves? These curves play a crucial role in the study of transport properties, diffusion, and scales in the chaotic sea, among other applications. And how can we find these curves in the phase space? How analyze curves? Several techniques have been proposed to investigate the behavior of invariant curves, some analytical and others numerical. However, many methods present complex mathematics or are expensive from the computational point of view. So our proposal is to present an alternative method to analyze these curves. And the inspiration for this study was the paper on Slater's criteria for the breakup of invariant curves. In this paper, the author studied the last invariant curve for the standard map. But what does Slater's theorem say? The theorem says that for an interval of size delta of a quasi-periodic trajectory, there are at most 3 different recurrence times, GAM1, GAM2, and GAM3 equal GAM1 plus GAM2. In addition, the theorem says that these times are related to rotation number of the orbit. And these numbers appear in the continued fraction expansion of the rotation number. To clarify this idea, I show here the continued fraction expansion for an irrational number, and here a short notation for this expansion. And the table 1, I have some approximations of the continued fraction. For example, here I have first approximation for this number. This number is the golden mean or the golden number. Here I have the first approximation, second approximation for this number, and so on. It's interesting that when we look at the denominator of these fractions, we get the well-known Fibonacci sequence. So according the Slater's theorem, if an orbit has rotation number equal to the golden mean, the recurrence times should be part of the sequence. If the interval, recurrence interval is large, I get smaller times. But if the interval is small, I have the times are longer. It is better because the approximation is better. So in this case, I need a small recurrence interval and bigger times, recurrence times. To exemplify, to illustrate this idea and this method, we have here the well-known standard map. Here the parameter k as the parameter that controls the transition for integrable to non-integrable behavior. Here is the phase space of the standard map for k equal 0.97. In this case, we have a mixed phase space with scales, islands of stability, and invariant spanning curves. We say spanning because these curves go across the phase space from one side to the other. It is known that the last invariant spanning curve for the standard map, that is the most robust curves, has a rotation number equal to the golden mean. So, according to the theorem, the recurrence times for this curve are only 3, and the rotation number equal to the golden mean, and these times are part of the Fibonacci sequence, as we saw in the previous table. To find these curves, we need search for points in the phase space that recurrence times are part of the Fibonacci sequences. And for this, I fixed the theta value and varied the variable I and search for these times. For each pair theta and I, we defined a recurrence interval and calculated the recurrence times. When we find only 3 times, and these times are part of the Fibonacci sequence, it means this point belongs the curve, and I found the last curve for the model. In figure B, it is just a zoom of the neighborhood of this curve. We can see some structure close to the curve, some islands and others invariant spanning curves. In this table, we show the recurrence times for found for previous curve. For the recurrence interval equal to 10 to the minus 3, we found 3 times. All of them are part of the Fibonacci sequence, and this gives the position of these curves. For delta equal to 10 to the minus 4, since the interval recurrence is smaller, the times are longer, but they still belong the Fibonacci sequence. In fact, the largest one is the sum of the other two times. To find the critical parameter for this curve, that is the value where the curve is destroyed, we repeat this process by subtly change of the value of the parameter. That is, I increase the parameter k and search again for these 3 recurrence times until the 3 times are no longer observed. Doing this, we have this critical parameter for this map. Note that this value is very close to the one found in the literature using other methods. This shows the accuracy of the method. Now, since the method worked well for the standard map, we applied in the others model. The first one is the Fermi-Ulam model. The Fermi-Ulam model consists of the particle collide with 2 rigid walls, one fixed and one move periodically in time. This equation that model of the system. In this case, epsilon is the control parameter. This is the phase space for the Fermi-Ulam model. Again, we have the mixed phase space. In red, I highlighted the curve was found using Slater's theorem. Here, we have the 3 recurrence times for this curve, and also below the Fibonacci sequence. Next, I found the critical parameter for these curves. In other words, the value where the curve is destroyed. But it's important to say that unlike the standard map, the Fermi-Ulam model doesn't have the last invariant curve because when this curve is destroyed, we have other curve here and here and so on. But no matter the parameter value, there are always invariant spanning curves in the phase space for the Fermi-Ulam model. But this specific curve is the last one to be destroyed in this region in his neighborhood. To exemplify, to clarify this idea in this figure, we have a zoom, a magnification of the region near the invariant curve highlighted in red, the same curve the previous figure. And in figure A, before the critically, we can see here the red curve and some blue curves. These curves are found using Slater's theorem. But in figure B, we have the same region, but for epsilon equal to the critical parameter. Now, all the other invariant curves are destroyed. Only red curve remain. That means this curve is the most robust in this region. In this figure, all curves highlighted here were found using Slater's theorem. They are the most robust in their neighborhood. In figure B, I just assume a magnification show the red curve is the first variant spanning curve among the most robust curves. In this table, we show the rotation number for each curve highlighted in a previous figure. Note that all curves have a rotation number equal to the golden mean or a shift of this value. That is why these curves are the most robust curves. Here, we have the critical parameter for each curve highlighted in previous figure. That is the value where they are destroyed. Not that the first, the curve 1 is destroyed first, then curve 2, then curve 3, and so on. Now, we extend our study to a family of Hamiltonian maps given by this equation. This is the same map presented by Professor Edson. By changing the parameter gamma, we can recover other well-known maps in the literature. For example, when gamma equals 1, we recover the Fermi-Ulam model. When gamma equals 3/2, we recover the Kepler map, and there are other possibilities. Next, I will show some results for different values of gamma. First, for gamma equal 1/2, we highlight these three curves here found using Slater's theorem. Here we have the three recurrence times for these curves. Now, in this table, we show the position of each curve as well the rotation number of which one. Note that their rotation number are equal to the golden mean or a shift of this value. That means these curves are robust curves in this region. Here in this graph, we show the relation between the rotation number and the position of the curve in the phase space. Note that the slope is equal to the gamma parameter. For gamma equal 1, we have a similar behavior. We highlight here 5 curves, and this is the recurrence times. Again, in this table, we show the position of each curve and the rotation number for each one. Once again, the relation between rotation number and position of the curve. Again, the slope is equal to the parameter. Now, for gamma equal 3 over 2. We highlight again 5 curves found by Slater's theorem. Here again are the recurrence times. These tables summarize the position and rotation number for each curve, and the rotation number again are equal to the golden mean or a shift of this value. In this case, it's important to say again, these curves are the most robust in their neighborhood. And again, we show the relation rotation number is position of these curves, and again, slope is equal to the parameter. And finally, gamma equal to is behavior is similar. I highlight here 4 curves found using Slater's theorem. Here, position of each curve and rotation number for each curve. And here, a relation between rotation number and position of these curves. Again, slope is equal to the parameter. As a conclusion, the results found so far suggest that the rotation number and the position of the curve are related by this equation. So if you know the rotation number, you can find the position of these curves, or if you know the position of the curve, you can find the rotation number. And finally, I will apply the method type of billiard. The research model is known as oval billiard. The boundary of this billiard is described in polar coordinates by this equation 4, where epsilon is the parameter and P controls the deformation of the billiard. Here, we have 2 examples of trajectory for different parameter combinations. In figure A, with this set of parameter, we have a trajectory that follows the boundary of the billiard. In this case, this corresponds to an invariant curve in the phase space. In figure B, with another set of parameter, the trajectory starts near the boundary, but after a few iterations, it changes. In this case, this trajectory is related to chaotic orbit in the phase space. But what are the conditions for the invariant curves to exist? We found in the literature that for epsilon above this critical value, invariant curves no longer exist. This idea is related to the concavity of the billiard. Convex concavities don't allow this type of behavior. To illustrate this idea, in figure A, we have the phase space for P equal 2. According to this equation, for p equal 2, the critical parameter is equal 0.2. So in figure A, we have the parameter larger than critical parameter. Before the critically, the red curves correspond to the orbit shown in the previous figure. In figure B, for p equal 2 and critical parameter equal to 0.3, in this case, epsilon is greater than the critical parameter, and all the curves are destroyed. So our proposal is to use Slater's theorem to locate these curves and determine the critical parameter above each curve are destroyed. Then we compare these results with results found in literature, that is, compare with equation 5. In this figure, we have a zoom of the upper part of the phase space of the oval billiard for p equal 2. We highlighted here 4 curves found using Slater's theorem. In this table, we show the 3 recurrence times for each curves, and not that the largest time is equal to the sum of the others 2. And now the idea is increasing the parameter and look for curves until none is found to determine the critical parameter. Here in figure A, we have the phase space for epsilon is equal the critical parameter that found via Slater's theorem. It seems that all curves are destroyed, but when we zoom in, we can see some structures, and the last curve is highlighted in red. Again, for p equal 3, in figure A, we have the phase space for epsilon less than critical epsilon, where we highlight for curves determined by Slater's theorem. And figure B, we have the phase space for epsilon is equal the critical epsilon, and the last invariant curve is highlighted in red. Here in this table, we summarize the value for p equal 2 and p equal 3. In the third column, the exact value given by equation 5, and second column, the value found by the proposed method using Slater's theorem. In the last column, we have the comparative error for these results. Now, we repeated the procedure for different values of p, and we compared the results with the equation 5. Note that the numerical results fit well with what was predicted in the literature. So finally, some of our conclusions. We use Slater's theorem as a theoretical basis to develop a numerical method capable to locate these curves and determine the critical parameter for this kind of curves. The results obtained demonstrate the effectiveness of the proposed method and agreement with the analytical results present in the literature. We believe this is a robust tool to find invariant curves and determine a critical parameter. We believe that it's possible to apply this method to non-twist models and analyze curves shearless. I would like to thank the partner of this research and the event organized for invitation and Professor Chris for invitation. Thank you very much.
Thank you very much, Joelson. That was a really very nice and interesting presentation. And I would like to ask now the attendees whether they have some questions they would like to discuss with Professor Joelson. Is there any question? Feel free to write your question in the chat box. Okay, I think there is no question from the attendees. So I was thinking of two questions that probably the second one is directly related to what Professor Leonel also presented. So my first question was more about practical aspects of this work. I think this is a very nice example how one can use theoretical results to help study the dynamics of chaotic mappings, for example. So I would like to ask, what is the approach to really compute these invariant curves coming from the predictions from the theorem? Because you showed results coming from numerical as well as theoretical computation. So how are these actually computed, numerically and also theoretically?
I think is numerically is easy to found and fast if you compare to theoretical number. In this case, I prefer numerically because it's fast and simple application.
Okay, so how exactly, what one should do numerically to compute these curves?
I think is the numerical result is very close to the exactly result is very close to the theoretical results, and is for me is very simple to apply. I don't know if is the question, but the numerical result is very close to the exactly results.
I can help on the answer. I can help on the answer, Chris.
Okay.
If you allow me. Well, what Joelson did indeed is the following. If think about this Fermi-Ulam model as a typical example. So if you go first order, you can approach where is the first invariant spanning curve is on the phase space. That is the approach used to characterize a global to local chaotic transition. Well, this is typical from the standard mapping where you have global chaotic diffusion or not, right? And then this allow you to estimate where the first invariant spanning curve is. Okay, since you have more or less the location of the curve on the phase space, then you go numerically with a very small step length seeking where this invariant spanning curve is. Well, once you have a glance where this curve is, and then you are averaging the number of interactions the particle has to recur within a given interval. So what you do exactly is divide the phase space in small windows along of the curve, and then seek what is the number of interactions the particle or the map needs to return or to recur within that window. And that is the what exactly Joelson did. So as soon as you increase the window, the number of recurrency reduce. So if you go for a small window, the number of recurrence becomes large. So if you are really on an invariant spanning curve, which is obtained by this golden mean number, which I also mentioned, it is one of the most robust curves. So you change the country parameter, the phase space changes, but the curve is still robust there and is not destroyed somehow. But the smaller the interval on the spanning curve, the larger the recurrence time is. And then Joelson plays with the size of the window within the invariant spanning curve. And then it moves along of the Fibonacci sequence. If the window is small, you can get long numbers on the Fibonacci sequence. That is what he did.
Okay, so that's a numerical approach, right?
Yes, numerically.
Yeah.
As I mentioned, the first approach is theoretical in the sense that he uses a transition from local to global chaotic dynamics in the standard mapping to describe locally the mapping and estimate where the first invariant spanning curve is. That is somehow theoretically obtained, but to determine exactly where the invariant spanning curve is, I'm afraid to say, but this is numerical and very expensive methods indeed.
Mm-hmm.
Very expensive numerical simulation.
Yeah. So it's a combination of theoretical and numerical approaches.
Yes, yes.
But essentially, Slater's theorem helps you have a good estimate where these last invariant curves are and how to find them, right?
Exactly.
Yes.
Yeah. Otherwise, so that's actually I think the usefulness of this theorem. If you didn't have this theorem, you would just shooting in the dark, right? You wouldn't know where exactly to go and find these invariant curves. But Joelson showed us many examples where this could be done because of the theorem.
Well,
Yes, exactly.
interestingly is that when you are studying, let's say, chaotic diffusion, the question is, where is the bound for the chaotic diffusion? The bound for the chaotic diffusion is, of course, an invariant spanning curve. But the question is, where is the first? What is the first invariant spanning curve? Is the first invariant spanning curve the one who follows Fibonacci sequence in terms of the recurrence time? So Slater theorem came to answer basically this kind of question. And it gives, okay, so you are on an invariant spanning curve. Okay, if you apply Slater theorem or Slater criteria, you see that it could be the first or not the first invariant spanning curve. It could be responsible to limit the bound of the chaotic diffusion or not. So Slater criteria is strong on this sense to define what is the bound of the chaotic diffusion somehow.
Yeah, okay. And my final question is, I think this theorem is applicable to two-dimensional mappings, or is it applicable to higher dimensional mappings? We know that these last invariant curves are basically curves in two-dimensional maps, right? But they become surfaces or higher dimensional surfaces in higher dimensional maps. Is this theorem still valid for higher dimensional maps, higher than 2 dimensions?
I think it is only two-dimensional maps because it's hard to define the recurrence interval when I have a high dimensional map. For this, I think is possible to use the Slater's theorem only two-dimensional map, I think.
Mhm. All right. Okay. Thank you very much, Joelson and Professor Leonel. Any questions from the attendees? I think there is one. So again, it's Kumar. Thank you so much, Kumar. So Kumar is asking, which disciplines do you believe could benefit most from collaborating with researchers in nonlinear dynamics? Also, what advice would you give to young researchers who want to enter this area of mathematical physics and integrate medicine, biomimetics for interdisciplinary or cross-disciplinary research?
Well, thank you for the questions. I think to begin to study this field, in my case, I think know about programmation is because the mathematics are no complex in this kind of the study. For example, in this study that I presented here, the computational part is more important than the mathematical part because the mathematical related this topic is very very simple. I think learn more about the program and language of, for example, Python or other language of program can help you to research in this area.
Mm-hmm. Yeah, and I think another example that comes to my mind, Kumar, is probably related to particle physics, for example, particle accelerators, where dynamics are mainly described by mappings, in some cases two-dimensional mappings. In that field, it's highly important that the particles are confined within a specific region of the accelerator, right? So probably this idea that Joelson discussed today is very helpful to them because it will help them identify the regions and probably make them able to control the particle accelerators and the particles without having damages or anything. So I think that's another example of where this work would probably apply. I'm not an expert on particle physics, but they might still be able or doing that. But that's just an example that can answer your question, which disciplines could benefit from this kind of work, for example, that Joelson presented today. Probably there are more examples from other disciplines or other fields, especially fields which are using mappings or two-dimensional mappings. Yeah, so thank you very much. If there is no further question, then I think we could move to the last presentation today by Dr. Mateusz Rolim-Sales, who will be talking about recurrence time entropy as a diagnostic for stickiness in weakly chaotic dynamics. Thank you very much, Mateusz. The stage is yours now.
Thank you. Can you see my screen?
Yes, we can see it.
Okay. Oh, thank you. Thank you for the invitation to present my work here. Yeah, I'm going to talk about recurrence time entropy. I'm going to talk a little bit about Slater's theorem again. I didn't know Joelson was going to talk about that, so you're going to hear that twice today. Yeah, I'm going to start talking about the standard map, which was the system we used for, well, developing this recurrence time entropy. And when we talk about weakly chaotic dynamics, we often talk about two-dimensional area-preserving maps. And the standard map is probably one of the most studied, like, two-dimensional map. It features all the characteristics of Hamiltonian dynamics, of two-dimensional area-preserving maps, and it's very simple as well. It has only one parameter, the parameter k, which controls the non-integrability of the system. For k equal to 0, the system is fully integrable. Here in figure A, we have the phase space of the standard map for k equals to 0. Every orbit lies on periodic or quasi-periodic tori. And these lines here are the quasi-periodic ones, and the periodic ones would be dots here, so we can really see them. And if we increase this parameter, the rational tori are destroyed, the tori with rotational number that are rational numbers, they are destroyed, and they leave behind a set of elliptic and hyperbolic points. This is the Poincare-Birkhoff theorem. And on the locations of the elliptic points, we see the islands of stability, which is these white regions here. And around the hyperbolic points, we see it's where the chaotic dynamics emerge from the stable and unstable manifolds of the hyperbolic points, which is the dark points here. So this value here is 0.9, which is before the last invariant curve is destroyed that Joelson just talked about. So after that value, we have the scenario of global stochasticity, which is the other figures. And if we keep increasing the perturbation here, more and more islands are going to be destroyed until eventually we can see almost no island in phase space of the system. And this behavior here is typical for any two-dimensional area-preserving map. So I put here a representation of the phase space of a typical two-dimensional map. We have here in gray the chaotic sea that I just showed you. In white, we have the islands of stability that are foliated with KAM tori, which are the thoris that haven't been destroyed by the perturbation yet. But when the perturbation becomes strong enough, these KAM tori are also destroyed, and they leave behind the cantorus, or the cantori, the plural. And these KAM tori in two-dimensional maps, they are barriers to the transport of chaotic trajectories. So a trajectory inside an island will never reach the chaotic sea, and vice versa in two-dimensional systems. So while the KAM tori are full barriers to the transport, the cantorus, they are partial barriers because they have this kind of holes in it. So the trajectory can actually pass through the cantorus and then reach the chaotic sea. And a chaotic orbit that approaches a island can eventually become trapped around this region bounded by the cantorus. So it enters this region, and when it's trapped there, it becomes a little bit less chaotic. So that's why we call it weakly chaotic dynamics. The Lyapunov exponent of the orbit diminishes, but it's not zero, it's positive. So the orbit is still chaotic, but it's a little bit less chaotic. And this trapping in this structure here, Professor Denis mentioned it, it's the Stickness effect, that it's probably the most fundamental characteristic of two-dimensional area-preserving maps. And the trajectory can enter and leave this region bounded by the Cantor rules infinite many times. As long as you keep iterating the orbit, it will continue to happen, and this causes an intermittent behavior in the dynamics of the orbit. The Professor Dennis showed that you can see a power law decay for longer times in the survival probability. You can see a power law decay in the recurrence times distribution. So this effect affects many statistical properties of a chaotic system. And the Lyapunov exponent is a good measure to quantify the thickness effect, but here we use it a different approach. We use the recurrence plots, which is simply the graphical representation of recurrences of a time series in phase space. So if we have a time series xi, where in a d-dimensional space, so here you can have a d-dimensional system, where n is the length of the time series, we define the recurrence matrix as equation 2. So it's defined like that mathematically, but if we think about it, it's simply we are comparing the state of a time in a time I with the state of a time j. If these two states, different states, they are close to each other up to a distance epsilon, then we say that this state is recurrent. And when we define the recurrence matrix like that, the value 1 corresponds to, this is a binary matrix, the value 1 corresponds to recurrent states, and the value 0 corresponds to non-recurrent states. This term here is the distance in the phase space. So in terms of a norm, in this work here, we use the maximal norm, but you could use any other norm. We just use that because it's faster numerically. And the threshold, I'm going to talk a little bit later, okay? So here in this figure, I have 3 different orbits for the standard map, the blue, the red, and the black one. And figures B, C, and D are the corresponding recurrence matrix. And the vertical and the horizontal axis is time. So we have 1000 iteration for these 3 orbits. And every dot we see here is a recurrent state. So figure B corresponds to a quasi-periodic orbit, which is inside the island here. So the recurrence matrix of a quasi-periodic orbit are characterized by long diagonal lines. We see some kind of dots here, and they are only here because the quasi-periodicity of the process. If we keep iterating the orbit, all of these dots will fill the diagonal line. So regular dynamics are characterized by long diagonal lines. In contrast, we have the chaotic orbit in black, which is, we see some structures here, but they are nowhere near the regularity of the quasi-periodic recurrence matrix. Meanwhile, the red orbit here, it's a chaotic orbit, but it's a chaotic orbit that it's trapped around this period 6 island here. So we know that if we keep iterating this orbit, it will eventually leave this bounded region to the chaotic sea, then it will be a fully developed chaos. But at this time, at least 1000 iterations, it's still trapped here. So we see that even though it's chaotic, the recurrence matrix is not as complex as this one, but not as regular as the recurrence matrix B. So the sticky orbit, the dynamics of the sticky orbit seems to be in between the regular one and the chaotic one. This is the characteristic of the weakly chaotic dynamics. So if the recurrence matrix can distinguish between these 3 behaviors, then we can use measures from recurrence plots to quantify this dynamics, right? And the collection of measures of recurrence plots are called recurrency quantification analysis. And the most common recurrence quantification analysis measures are the recurrence rate, which is simply the density of recurrent points, which is so the number of recurrent points divided by the total number of points in the matrix. The determinism, which is the density of points along diagonal lines. So a fully regular periodic orbit will have determinism equals to 1 because all points are on diagonal lines. And these references here are some works that has been done using these two measures to quantify thickness. And we can also have the entropy of the line. So in a recurrence plot, we can have diagonal lines, which I just showed you. We can have vertical lines, and we can also have vertical white lines. The vertical white lines are simply the distance between the vertical distance between two diagonal lines. And then we can, P here can be the distribution of these lines, the relative distribution of these lines, and we define the Shannon entropy of this distribution. So this can also help us identify not only thickness, but all kinds of behavior in the system. So yeah, the vertical distance is important because it is the return time of the orbit. If we think that at some time I, the orbit was in some state, at a later time j, at the next diagonal line, it goes back to that state. So it means that this distance, this vertical distance, is simply the time it takes for the orbit to return to that state. So this is essentially the definition of the return time or the recurrence times. And because of Slater's theorem that says that quasi-periodic orbits can have at most 3 different return times, where the third one is the sum of the other 2, and Joelson talked about a little bit more of other properties of these times, then it's possible to distinguish between regular orbits and chaotic orbits by simply counting the number of unique return times of an orbit. So we initialize a initial condition at some point, we define a square region around that point, and we count how many times the orbit returned to that point and how long does it take for the orbit to return to that region again. If we only see the orbit returning at one time, for example, at every 10 times, the orbit will return to that point. So this is a periodic orbit of period 10. If we see more than, if we see 3 different times, the orbit is quasi-periodic, and if we see more than 3, the orbit is chaotic. So just to exemplify a little bit better this, we have here 3 different orbits, the blue one, the green one, and the red one, still for the standard map. And we did what I just told you. Given the initial condition, we defined a square around that initial condition and count the return times to that point for different recurrence regions. So the first one is 0.05, the length of the square is 0.05, 0.025, 0.01, and 0.005. So in the right-hand side here, we have the histograms of the distribution of the recurrence times. And we see that regardless of the size of the region, there's always only 3 columns of each color. And here are the times we get. And the third one is always the sum of the other 2. The smaller the region, the larger are the recurrence times because, well, it's more difficult to get there. So it's natural to expect that the time increases as the region diminishes. So yeah, this is basically Slater's theorem, and so we can use that to distinguish between chaotic and regular solutions. Here we did the exact same thing, but in the total phase space of the system, and the islands here are corresponding by the blue color. They have only 3 unique recurrence times. So the number of each recurrence times can change. Like if we go back here, if we iterate for a little bit longer, the height of each one of these bars will change, but there's only 3 of them. So we counted the number of unique recurrence times here. So yeah, we see that the islands are corresponding by have 3 recurrence times. So with the blue color, the gray red color here corresponds to way more than 3 recurrence times, which is the chaotic dynamics. And we know that around the islands we have this thickness effect, and we see that the number of unique recurrence times it diminishes. It's not as large as the chaotic one. So there's some indication that this can help us detect this thickness effect. But the number of unique recurrence times alone, it's not good, because if we keep iterating, we'll keep finding more and more recurrence times for chaotic orbits. And then we can have, for this, below this value, we have the thickness effect. So instead of using the raw number of unique recurrence times, we take the distribution of return times using the recurrence plots. So we generate the recurrence plots for a orbit. We count the number of white vertical lines, which is which are the return times of the orbit. And then we define this probability distribution for the white vertical lines. So yeah, instead of iterating the orbit for a long time, we instead use the recurrence plots to do that for us. So we can use fewer iterations, and we can also use that for experimental data. So the recurrence time entropy is defined by equation 4, which is PW here is the distribution of white vertical lines that I just mentioned. And actually, the recurrence time entropy was first defined with no relation to the recurrence plots. It was using the method I just described. But here we are using the recurrence plots. So a periodic orbit, which has only one return time, will have a recurrence time entropy of 0, because we will have a distribution of only one number, which the entropy of this distribution is 0. The quasi-periodic orbit will have a small recurrence time entropy, because we have only 3 return times, even though the height, the proportion of the probabilities changes with time. It's still only 3 of them, so it's a small value, a small entropy. And the chaotic orbit that can have more than 3 return times will have a large recurrence time entropy. And for stick orbit, then we expect a smaller RTE than for chaotic orbits, but larger than it would be for a quasi-periodic orbit, because we have seen that the recurrence plots are in between these two behavior. So to check our assumptions, we computed the largest Lyapunov exponent for the standard map in phase space of the standard map here in figure A. Figure B is a magnification of this white square. And here we have the parameter space as a function of the parameter k of the standard map. So the Lyapunov exponent, we know larger than 0 is chaotic. In our case, quasi-periodic and two-dimensional area-preserving maps, the regular orbits are characterized by a 0 Lyapunov exponent, which is the black color here. Well, it's not actually 0, it's going to 0. And in the bottom row, I calculated the RTE for the same conditions, for the same time iterations, and we see that they agree very well. In the chaotic region here, we have a large RTE. Inside the islands, we have a smaller RTE. And in between the period 6 island and the chaotic seed, that we know that's a huge thickness region there, the RTE is not as large as the red color, but it's larger than the blue color. So yeah, the RTE is a great alternative to the Lyapunov exponent to well, characterize the behavior of the system, if it's chaotic, if it's regular, etc. And now regarding the threshold that I mentioned before, it's very important to define it. Usually that's a very important parameter when we're dealing with recurrence plots, but in our case is not as important as in those cases. I showed you that regardless of the size of the region, there's only 3 recurrence times, even though the number changes, but there's only 3, so it's not as important as in other cases. But just to make sure, we computed the threshold as 10% of the standard deviation of the orbit. And here in figure A, we have the standard deviation as a function of k for 3 different methods, because we have a 2-dimensional time series. So how do you compute the standard deviation of a 2-dimensional time series? Well, the first approach, the black one here, we just take the x time series and the y time series and concatenate them and compute the standard deviation of this 1-dimensional time series. Well, in our case, this works very well because the theta and p coordinates are in the same range from -pi to pi. But in some cases that you have like -pi to pi and -infinity to infinity, this could lead to some bias in the standard deviation. So that's usually not what we want. And the red and the blue colors here, we considered a standard deviation vector. So we computed the standard deviation of the x time series and the y time series. And if you have more than 2 dimensions, you can have like a d-dimensional standard deviation vector. And then we compute the norm of this vector. In our case, we use the maximal norm as well, both for the recurrence plot and the threshold. So we see that they are kind of the same value here. So, and then we use the 3 of these methods to compute the RTE and the Lyapunov exponent, and we computed the Pearson correlation coefficient between the RTE and the largest Lyapunov exponent as a function of this threshold. So this is in units of the percentage of the standard deviation. So here is 1% of the standard deviation, here is 5%, 10%, and 15%. So we see that there's a whole range of values for the threshold in which the correlation coefficient it's high, it's almost 1. So yeah, we chose 10%, which is here, but you could choose 15, you could choose 5%, so it doesn't really matter in our case, okay? So yeah, we show that the stickness effect is characterized by a Lyapunov exponent less than the largest in the chaotic region, the RT the same thing. So instead of computing these quantities for a very large iteration time, like 10 to 8, for example, I don't know, we instead compute these measures in windows of finite time. And by finite time here, I mean very small times, because numerically every time is finite time, right? So we, instead of compute for a long time, we follow the trajectory for a very long time, but computing the RTE for in windows of size n, which in our case, we use it 200 iterations. So in this way, we can clearly see when the trajectory is in the chaotic C and when the trajectory is trapped. So because this would give us different values for the RTE. And when we do that, we get this time series here, for example, in the inset. So when we have this highly oscillatory behavior for the RTE, the finite time RTE, it's when the trajectory is in the chaotic C, which it's not trapped. And then we can see this, suddenly the value of the RTE goes very small, and here we can see a different one. So these this region, this windows, it shows when the orbit is trapped around the islands, when it's trapped in the sticky regions. And when we compute the distribution of these values here, we get this distribution in figure A. So we have this multimodal distribution where this highest peak here corresponds to the times when the orbit was in the chaotic sea, and these smaller peaks here corresponds to different trapping regions in phase space. And to see which one of these trapping regions is located in the phase space, we select these 4 colors here, and we plot in phase space the regions, the phase space points that generated each one of these peaks here, and that we can see in figure B and C. And figure C is a magnification of this square here, rectangle. So yeah, we can see that each one of these colors here corresponds to a different hierarchical level in this structure of islands around islands in the phase space of the system. And the smaller the RTE, the inner is the structure. Yeah. So when the orbit enters a trapping region, it can enter an even more like an inner region within that trapping region, and so on until for infinitely small scales. So this is what gives rise to this multimodal distribution, and the RTE can characterize that very well. And just to, oh no, before that, we can also compute the distribution of trapping time. So we can also count how long is this windows that we see here. We know that for fully chaotic systems, the trapping, not really a trapping when you have a fully chaotic system, but we know that the distribution of recurrence times is a exponential decay. And when you have a stickiness effect, the distribution becomes a parallel decay. And it's what we see here. We don't see like exactly a parallel, but we see regions where we can distinguish very clearly different parallel decays because we have different hierarchical levels. And when we compute the trapping times in the chaotic sea, when corresponding to this peak here, we see a exactly exponential decay. So again, using the RT, we can then measure these times. And just to compare with the Lyapunov exponent, which was like the most traditional approach to chaotic dynamics, we have here the distribution of finite time Lyapunov exponents, and here the distribution of RTE. And the Lyapunov exponent does detect the stickiness effect, but we don't see this multimodal distribution as we see with the RTE. So if you want to see if there is stickiness in the system, you can use the Lyapunov exponent, but if you really want to characterize which one of these hierarchical levels, you must use the RTE. And just to test with a different system, because everything works usually with the standard map, so we chose a more practical problem, which is the drift motion of passive particles. This is a plasma physics problem. I'm not going into the details of it, just that it's a very complicated map, but each one of these parameters here, alpha, gamma, all the Q's, U, and V, they are fixed. So they are measured from experiments in the tokamak in USP. And the only free parameter is the epsilon here, which is the corresponding to the perturbation here is in the same way we had in the standard map, we have the K parameter. So again, we have 3 different orbits here, the blue one, the black one, and the red one. The blue one is the quasi-periodic one, the black one is the chaotic one, and the red one is, it's quite small here, but I think you can see it's the trapped one, it's the sticky orbit. And we see the same behavior, a very regular recurrence matrix, a very complex recurrence matrix, and here's something in between. And when we compute the finite time RTE, we again see this multimodal distribution, where each one of these peaks here corresponds to a different hierarchical level in this structure here. And the recurrence time, the distribution of trapping times is also a power law. Here's a much more nice power law decay here. And again, here we see the exponential decay. And so just to conclude, the RTE is positive correlated to the largest Lyapunov exponent. So it's possible to distinguish between chaotic and regular solutions. So if you have a system with a high Lyapunov exponent, you expect a RTE high as well. It's a great alternative to detect different dynamical behaviors. And there's some kind of open questions. That's something that we want to do, we haven't done yet, which is use the RTE to characterize the phase space of dissipative systems, and the RTE to characterize the dynamics of higher dimensional systems. There was a question about Slater theorem being able to detect in more than 2 dimensionals. Well, there's no, it hasn't been proved. It has only been proved for 2 dimensionals, but there's some kind of indications that there is a minimum recurrence time for number of recurrence times for higher dimensional system. So if that's true, then we can use the RTE for higher dimensional system as well. And it would be interesting to define an upper bound for the RTE. So the values would be between 0 and 1. So which would be much easier to say, oh no, this value here is the quasi-periodic one. And also use the RTE to characterize experimental data. If we have some circuit or something like that, then use the RTE to, well, characterize the data. Yeah. And just some advertisement here. Some colleagues and I recently published a Python package for dynamical systems. It's very easy to use. It's very fast. It's we have have implemented many methods there. You can compute the trajectories, you can compute the Sally, Gali for chaos detection. The RTE is there as well. You can compute the statistical measures that Professor Denis talked about a little bit ago. Periodic orbits, you can compute their manifolds. We also included some Bayesian metric for quantifying the structures of Bayesians of attraction, such as the Bayesian entropy and the dimension of the Bayesian as well. The paper is still under review, so you can, if you want, you can check out the preprint in archive. The documentation is on this page here. You can email me if you have any questions. So, yep, please check that out, give the input, use it. And that's it. Thank you. Thank you very much for your attention.
Thank you very much, Mateus. That was really fascinating presentation. There are 2 new questions in the chat box, so I will go through the first one by Emiliano. So Emiliano is asking about figure 1 that you presented. So if we can just go back to the slide with the first figure. He's asking what happens to the function when k takes on prime numbers. I guess it's this one, yeah.
Yeah, there's not really a difference there. If k is large enough, then we expect something like that in figure F here. For the larger the k, the less are the size of the island, the smaller is the size of the island. And then we see simply only a huge chaotic orbit filling almost the entire phase space. Yeah, there's no, yeah, it doesn't really matter if it's prime, if it's irrational, if it's, yeah.
I think the most important aspect with respect to K is the critical value after which you
Yeah,
have the
yeah,
destruction of the
0.97, yeah.
where you see gradually the appearance of global dynamics, chaotic. All right. Thank you very much, Mateus. Now we can go to the next question by João. Since Lyapunov exponents are closely related to symbolic spaces, can we do the same using RTE to build symbolic spaces to study symbolic dynamics?
But I don't know what symbolic states here are. So,
João, would you mind explaining your question more?
symbolic spaces.
Maybe symbolic dynamics?
Yeah, there's a paper, there's a PRL actually that uses the white diagonal lines, which he calls symbolic dynamics. Maybe that's it. So yeah, probably if you think you can make a parallel from white vertical lines to white diagonal lines. So yeah, maybe you can do that.
Yeah, João says that he's talking about symbolic dynamics. So a connection between symbolic dynamics and Lyapunov exponents and RTE, I think.
Yeah. Yeah,
All
I
right.
think so.
Okay. Yeah, please.
No, that's I think you can, but I don't know how.
Yeah, so it's still an open question, I think, right? Yeah. Okay, the next question comes from Chelsea. She's asking if a dissipative system can have an influence on the recurrence time. Does it shorten or lengthen it?
No, actually, no, it doesn't shorten, nothing like that. You have to have a bounded system, so you can, the recurrence Poincare theorem is valid. So you can have like an attractor in the infinite. But if you have a bounded attractor, then yeah, the Slater's theorem works for two-dimensional systems. And the only thing that changes the times is the size of the recurrent region. Yeah, that's only that.
Okay. All right. Is there any other question? Yeah, there is another one from Kumar. So Kumar is asking, what tools or methods do you use to find chaos in a system, and how artificial intelligence is bringing rapid progress in the computation methods, and what changes and challenges have you faced in experience with AI-based tools or computing methods in work?
Tools or methods to find chaos in a system. Well, the RTE is one of them. The Lyapunov exponent is one of them. Chris here worked very much with Sally and Gali, which are different measures to chaotic dynamics. AI, artificial intelligence is bringing rapid progress in the yeah, I haven't really used AI-based. What do you mean by AI-based tools like ChatGPT or computing method in work?
I guess machine learning probably, or related methods.
Yeah, I haven't seen anything done with machine learning with chaotic dynamics. What some people do actually is prediction of chaotic systems, which is nice. It's good to being able to predict for longer times the behavior of chaotic systems, but yeah, this is as far as I know.
Yeah, it's very interesting, and there is currently work being done by various groups around the world on chaotic prediction using machine learning techniques. It's very important in chaotic dynamics to overcome this problem of long-term prediction. We know that by construction, a chaotic trajectory is very difficult to predict after one Lyapunov time, which is defined by the maximum Lyapunov exponent of the system. So we're talking about unpredictability. This is one of the fields where data science approaches, in particular machine learning, has entered, trying to improve our ability to predict the behavior of chaotic dynamics longer into the future. Of course, it's not like a method that can, or approaches that can help us predict for an infinite amount of time, but it can extend the prediction horizon to multiples of the Lyapunov time, which is very promising. And I know there are people working on this, and we are also working with one of my PhD students on chaotic prediction and using machine learning techniques. That's Anthony. He's joining us today. So yeah, that's these are usually the kind of tools that have already started getting
Yeah.
into the business of dynamical systems, and it seems to be a promising one. So there is a cross-disciplinary approach on when it comes to dynamical system and chaos theory.
Yeah.
All right. I think we still have some more time. So if there are more questions, feel free to post them on the chat box, and then we can take it from there. Oh, Emiliano came back saying he means the numbers 1, 1.1, 1.3, fraction of prime numbers as 1, 11, 13, etc. If these make any difference when as the k parameter in the mapping.
Oh no, it doesn't. No. Yeah.
Yeah.
Like Chris said, the most important value here is 0.9716 something.
Yeah.
Which is when the last curve break. Then we have global chaos. Actually, there's an interval of 2 pi that small islands reappear again in the system. So if you compute the area of the phase space, you will see that every 2 pi of k, sometimes you see smaller and smaller islands appearing in the phase space. But yeah, that's only that.
Yeah, and I think another probably way of looking into this question would be to compute the bifurcation diagram as k increases and try to identify critical k values where you have the appearance of bifurcations like double
Yeah.
bifurcations and things like that. This might help someone associate these critical k values with prime numbers if there is anything hidden there. But I think that's not clear at the moment, right? It's probably something that still has to be done.
Yeah, there's a paper that from Joelson, he did this bifurcation diagram up to K1000.
Wow.
Yeah. So he showed that very small islands appear, but the only thing is this 2 pi that every 2 pi you see these islands.
Yeah. All right. Any other question from the attendees? If not, then I would like to thank the organizers again, the speakers again for these very nice presentations, and all of you attending the seminar today. Thank you everyone so much, and I hope it was a useful one. If you still have questions, I guess you can approach us by emailing us, and we will all be very happy to answer and discuss your questions and discuss with you. Before we close the webinar for today, Kumar is asking what free online resources would you recommend for learning more about this matter?
Our package has some explanations on that, so you can visualize the dynamics while reading about it. Yeah, but that's one thing I can think about.
Yeah, and I would add that it also depends on what exactly you want to study more. So
Yeah.
there are different kinds of books and resources depending on what you want to discuss. So if you have further questions, something that you would really want to discuss with us, feel free to email us. I guess Liliana, the attendees will be able to get in contact with us by sending us emails. So I hope they will have access to our email addresses, institutional ones, so that they can keep discussing with us if they want to.
Yes, that's a great idea. Thank you. I would like to thank the chair and the speakers for your valuable and interesting presentations. I think it was great, and I would like to, I'm also thankful to attendees and hope they found this useful.
Okay, thank you everyone and have a nice day.
And
Bye.
that would be
Thank
all.
you.
Yeah, so later you can
Goodbye.
get in
Thank
touch.
you. Bye-bye.
Have a nice day.
Have a
Bye.
nice day. Bye-bye.